Hello, this is Katherine Jones with Group 4, and I will be introducing our topic for the project. The following slide shows the breakdown of this presentation. It includes an introduction, a literature review, a BIM implementation plan, our project approach to collecting data, the results of our research, and our conclusions based on the results. The introduction will cover BIM for visualization of architectural design intent and spatial analysis. The literature review discusses the importance of our research, our implementation plan, and our approach to reviewing the literature. The BIM implementation plan outlines the 4 elements of an implementation plan. The project approach goes into more detail about how we collected our data and information. The results discusses what we found from our research, and the conclusion reviews what we learned from our results. Introduction: Using BIM and construction for visualization of architectural design intent and spatial analysis. This report focuses on utilizing BIM to achieve design intent and conduct a spatial analysis, resulting in a more cohesive final project that reduces potential issues with constructability before the construction phase begins. The primary BIM mechanic which can help facilitate this is in BIM's parametric design abilities. What is design intent? Design intent refers to the architect's specifications of the building form, layout of spaces, and functional characteristics to allow evaluation of building visualization and performance. Design and construction is a problem-solving process, where information is traversing through a network of project stakeholders. Because design is a nonlinear process, it requires appropriate design management to ensure design objectives and project target values are achieved. Poor management of the design process, possibly due to miscommunication within the project, has been commonly seen as a root cause of poor quality, schedule deviations, and cost misalignment in construction projects. This often exists in conventional design, where design has little integration with the construction and operation processes. Integration in design and construction becomes more crucial for implementation of novel technologies such as digital fabrication. Spatial analysis, for the purpose of this report, can be defined as the act of analyzing a space to determine how the elements within the space interact with one another. For example, analyzing a space in an existing room in an already built building may expose that an electrical outlet was halfway located into a window seat, or that a particular fixture was larger in real life than the designer might have imagined. The cause of such discrepancies may have to do with the fragmented nature of the construction industry, which can lead to misunderstanding and reduced productivity, and can be attributed to the incapability of designers to grasp the abstract concept of buildability. Spatial analysis and design intent go hand in hand, as analyzing a space and determining its intended use case drives the intent of design. The problem here is that it is difficult to document intent through the use of 2D software and data alone. In addition, another problem arises when a designer drafts out plans that are not feasible to construct outside of a computer screen or hand-drawn sketch. This drives the need for designers to implement spatial analysis at a higher level, not only to better document design intent for the purposes of delivering clear instructions to the construction team, but also in terms of preventing potential issues that are only found during the construction phase. This report aims to suggest BIM may be a viable solution to both those problems. It is BIM's parametric abilities that provide the most potential for improving quality of a final product through design intent and spatial analysis. Shown on the slide is an example of parametric modeling using a parametric object. Parametric modeling is a technique that involves creating 3D models using parameters, relationships, and constraints. It allows designers and engineers to build and manipulate 3D objects while maintaining control over various design parameters. A parametric object is a single object that is created or edited through its parameters and parametric constraints. Why does design, spatial analysis, and parametric modeling matter? They matter for a few reasons, including buildability and constructability of design, for the identification of design conflicts before construction begins, for improving collaboration between all disciplines, and allowing the construction team to provide better substitution requests and suggestions to the design team earlier in the design phase of the project, which may lower overall cost while maintaining quality workmanship. Design, according to the article Factors Affecting Buildability of Building Designs, suggests there is a consensus that the design stage is critical for implementing buildability or constructionability, meaning some designers, especially inexperienced ones, may take software such as Revit or SketchUp, or any other 3D modeling tool, and create wonderful and organic designs that most people can only imagine existing in real life. The problem is that these types of designs are difficult to construct. In the 3D space, designers are not bound by the restrictions that affect construction, such as general physics and implementation. They don't consider how difficult it may be for a construction worker to fit their tool into a tight corner, or blend a curved wall into a sharp corner. In most cases, such ideas of constructability are not considered. In other cases, problems of buildability may be less due to the inexperience of a designer, and can be partially blamed on the limitations of the tools available for them to perform a thorough spatial analysis. Limiting themselves to 2D software forces the designer and their consultants to rely on simple overlays to perform their analysis with. This may show a duct running through a room, but it will not show the duct running 2 feet below the ceiling unless the designer actively sketches out the conditions for all elements in that room, and every room they want to ensure has no conflicts. In the spatial planning stage, the first decisions to be made address the position of the building on site, the spatial form of the building, and the main materials of its external partitions, such as walls, the windows, and the roof. Therefore, the planner must establish these solutions in a format compatible with BIM. According to the BIM handbook, Building Information Modeling is a modeling technology and associated set of processes to produce, communicate, and analyze building models. BIM, as noted in the handbook, is characterized by building components that are represented with digital representations, which are objects, that carry computable graphic and data attributes, allowing parametric rules that allow them to be manipulated in an intelligent fashion. They include components that include data that describe how they behave, consistent and non-redundant data such as changes to components that are represented in all views that the component is in, and allows for the project team from design to construction to communicate and collaborate effectively and productively. BIM, with this definition, can contribute to both design intent and spatial analysis, especially through the use of its parametric capabilities. In fact, it is the parametric capability that may be the most useful in terms of preserving design intent and providing a thorough spatial analysis. This is because parametric features will propagate throughout the project and will allow both the designer and the contractor to review how a fixture may affect other features in the space that the fixture will be used in before making the decision to go with one or the other. This helps the contractor in terms of allowing them to make changes to their own model, performing their own spatial analysis, and then going to the designer in good faith, knowing that their fixture will act as a good substitute for the one the designer is proposing to use without making unintended changes as a result of being unaware of any conflicts when using this fixture. This is especially helpful when considering what size washer and dryer to include in your utility rooms, or which refrigerator to use in your units. Some may be too large, in which case it may be easy to try and swap out multiple sizes based on the appliances you're looking to use in your project. This type of analysis will allow both the designer and the contractor to maintain design intent and perform a meaningful spatial analysis of all the conditions of their spaces before it becomes a problem during construction.
Number 2, literature review. During our literature review, we considered what is important to our topic, which implementation methods we should use, and how we should approach our topic. In regards to what is important to our topic, we considered which points and terms were relevant to our topic. We also decided how in-depth our research should be and which types of sources we should use, such as information from the textbook and scholarly articles from databases. We chose to research 5 areas regarding BIM implementation methods. These included BIM in regards to architecture, BIM in regards to construction, how BIM can be implemented to increase coordination and collaboration, how BIM can be implemented to facilitate design intent, and how BIM can be utilized for better spatial analysis. When creating our approach for our literature review, we had to consider the time frame available for the project, and then structure out our research accordingly. In addition, we analyzed personal examples of BIM implementation from our own projects, and we researched existing case studies relevant to the topic. Here are a few of the personal examples that we considered during our research. You can use BIM to understand design intent, such as to help understand why a pipe was below the ceiling. You can also use BIM to measure features to understand spatial analysis. and using parametric modeling would help prevent issues such as a duct running through a doorway.
The BIM implementation plan is the document which details implementation on a step to be completed. And this document identifies the milestone of purchasing the BIM tools, developing modeling standard, and training for staff. In simple terms, it is a set of activities undertaken by an organization to deploy BIM tools related to workflow. There are 4 steps in implementing the plan for the BIM. The first element of the implementation plan is to identify BIM goals and uses. The BIM goals are to improve coordination and communication among project stakeholders in order to reduce rework and waste. Furthermore, in order to increase the accuracy of the construction document, in this day of age, projects are becoming more complex, and the need for communication and collaboration are needed. The second element of the implementation plan is the design BIM project execution plan. Mapping the BIM process for the project requires the project team to first develop an overview map which shows how the different BIM uses will be performed. The BIM overview map shows the relationship of the BIM uses, which will be the employer on the project. Also, detailed BIM uses processes map are created for each identified BIM uses on the project in order to clearly define the sequence of various processes to be performed. The third element of the implementation plan is to develop information exchanges. Every project does not need to be included for a model to be valuable. Therefore, it is important to only define the model components that are necessary to implement each BIM use. The different steps are information exchange, worksheet, identify each potential information exchange from the processes. Choose a model element breakdown structure for the project. Identify the information required for each exchange, meaning input and output, and compare input versus output content. The fourth element of the BIM implementation plan is to define supporting infrastructure for BIM implementation. We first must identify and define the project infrastructure required to be effectively implemented as a planned. First, the team should review and document critical project information that may be valuable for the BIM team for future references. The second step is for at least one representative for each stakeholder involved should be identified, including the owner, designer, construction, prime subcontractor, fabricator, supplier, tenant, and facility management, and supplier and manufacturer. Project approach. Due to the time constraint of the assignments, literature analysis and personal example were used as the data to support the paper. Both these allow for the documentation of existing issues, some of which have already been studied and addressed in multiple locations across the world, giving a wide berth to the validity of the ideas proposed in this study.
Number 5, results. There are many benefits of utilizing BIM on construction projects. These include it benefiting the workflow and scope, the craftsmanship and expertise, the knowledge and growth, and the integration and information exchange. Regarding workflow and scope, online dashboards enable firms to not only manage information, but also understand and control how information is generated, assembled, and distributed. Regarding craftsmanship and expertise, linking design information seamlessly with fabrication and construction processes allows for expanding craftsmanship and expertise. Regarding knowledge and growth, knowledge capture offers the flexibility to implement changes at any time, accelerating project delivery schedules and enabling future reuse and interoperability. Regarding integration and information exchange, cloud-based platforms allow all models and project information to be hosted remotely, facilitating the seamless exchange of information from diverse locations. In conclusion, nearly every phase of production in architecture, engineering, and construction is now digital. Project authorship being invariably collective, the importance of optimizing building information management is growing. New digital platforms have created a much faster and more efficient experience. Digital modeling software, building information management, and computational simulation have proliferated. The old linear process has now been replaced by a better connected digital engineering process. Expanding authorship requires platforms that adaptively integrate diverse sets of information, tools, and workflows. Project authorship in AEC is continually reshaped by new technologies. By implementing BIM, the following procedure helps the project. This slide contains our cited sources. Thank you.